Okay, let's say I have a substance and it has a half-life of, let's say it's 4 hours. Okay, and I have initially the activity, which we're going to call A naught. The initial activity is 5,000 becquerels. I could then answer questions like, what will the activity be in 8 hours time? And what we would have done at GCSEs is we would have gone 5,000. After 4 hours, one half-life, that would half down to 2,500 becquerels. And after another 4 hours, it would drop down to 1,250 becquerels. Okay. However, what would the activity be at 2 hours? Um, this method can't tell you that answer. Now, I could estimate that it's going to be somewhere in between these two values, but it's not going to be halfway because that graph that your decay curve is not a straight line. Um, it's a curve. It's going to drop more um, earlier than it does later. So if I did go halfway, I'd actually expect it to be slightly less than the value halfway between those two. So I might expect it to be about 3,200. But that method of just knowing the half-life doesn't work for all times and all activities, just very specific points in time. Therefore, at A level, what we do is we need an equation that can describe what the activity would be at any time t, and it is this equation. This is a decay equation. We see this numerous times in physics. In fact, probably next to direct proportionality, this is the most common physical relationship we see in physics. Um, so the activity at some time t is related to, well, I'll just write this all on. This is the activity at this time. This is the initial activity, i.e. the activity when the time is 0. That letter E is a constant. It's Euler's constant. You can type it into your calculator. What is it, 2.7 something or other? It's a constant. It's in your calculator. You don't need to calculate. You just use your calculator to get it. And this here then is our decay constant, which is constant for a particular isotope and has a big variation in terms of what values it can have. We'll talk more about that in a little second. If we look at that exact equation, we can repeat it essentially over here, only this is the number of unstable nuclei. This is the initial number at t equals 0, and everything else there's the same. So this is the time, and this is your decay constant. Now, if we then do look more carefully at this decay constant, so we do use the letter lambda. It's the same symbol we use for wavelength. They're totally different things. Okay, we just use the same symbol to denote them. It can be measured in per second, per minute, per hours, per days, and it depends really on how long the half-life of the isotope is. It's probably easiest to stick with this, but not always, and we'll show you examples of that in a little second. So the thing that links these two quantities together, the activity and the number of unstable nuclei, well, we should just expect that they're directly proportional. Because what we mean by that is, let's say I have a certain sample that contains some number n, and I use a Geiger-Müller tube to measure the radiation that's being emitted for that, and I get some activity A. If I have twice as much of that substance, I should expect that there'll be twice as many, twice as much radiation coming off it, and then my Geiger-Müller cube should expect to get twice the activity. So if you have double the amount of unstable nuclei, you should expect to get twice the activity off it. Therefore, I would say that A is directly proportional to N, and in maths, you would just replace that with a K. We like keeping our constants different, and that is just what your decay constant is. Now you will notice that when this equation is given in your data sheet, I think as well, it has a minus in there. Now, we'll maybe talk about this a little later when I'm actually in class. That's due to the mathematics of it. You can actually derive these equations up here from this. What we're saying here is that the effective activity is to reduce N. So if something is emitting radiation, N is decreasing, and that's why the minus sign is in there. You don't need to worry about that. Most of the time, we would just ignore the minus sign. Now we can rearrange that equation then to work out, well, what is the decay constant? Because if we rearrange that and ignore the minus sign, we get that it's A divided by N. Okay, and we can then say what that represents. Okay, because A is the activity, it's the amount of radiation that is given off a source in, say, 1 second. If we measure it in becquerels, so if I have something that is 300 becquerels, that means there's 300 pieces of radiation, be it alpha, beta, gamma, emitted per second. But then we divide that by the number of nuclei that are present. So that would be the amount of radiation emitted per nuclei per second, okay, because we've got this per second in our activity. So what that means is that if something has a bigger decay constant, it's going to decay more rapidly because we're going to see more activity per second per nuclei that is present. Okay, so for instance, if I have a lambda of 0.5 per second, and let's say I have 2000 unstable nuclei present, we can put that into this equation. You can kind of see what the lambda means. Activity is equal to lambda n is equal to 0.5 times 2000, which will give us an activity of 1000 becquerels. So really what you can think of this is it's the proportion of nuclei that we would expect to decay per second, okay, or per hour or per day or whatever it is we've measured in. Okay. So you can see we have the definition here for a decay constant. I would learn that off. So a larger lambda means that we have a more unstable nucleus. We expect them to decay more quickly, and it should have a shorter half-life. What we're going to do next then is we're going to look at these equations here a little bit more and how we use logs to help us manipulate those equations.